This conference will now be recorded.
All right. Whenever it works for you, please start.
Will do. All right. Thanks, Boppy. So we finally are able to pull this together. So what I want to go through today is a little bit about Crossfire, but a lot about chiplets in general, our experiences, and an elephant in the room that is there. I don't think a lot of people talk about, maybe not even recognize, which is the interconnect pitch gap. I first heard this phrase, actually I read about it in an article from 3D Insights. It was uttered by a TSMC exec at a conference keynote. And we've kind of latched onto it because it's something that we think Crossfire has a unique approach to solving. Now, for some reason, my screen won't. There we go. So just going to start out with a high-level view of what we want to talk about and kind of state the obvious. First, everyone knows that chiplets and chiplet technology have been around a long, long time. I think, the first ones probably came out in production in some FPGAs in 2014 timeframe. So not so much that they're there, but how do we make them more accessible? So unless you have really, really deep pockets and are one of probably 10 or 20 companies or a well-funded startup with some connections, the state-of-the-art chiplet technology, it's really hard to get access to. Current die-to-die IP interconnect chiplets is complex. It needs to be because there's a lot of work that needs to get done there. But one of the things that does is it adds complexity and challenge to some of the economic aspects because you are adding cost every time you break up an IC into chiplets. Now, sometimes you save costs in other areas, but that's kind of the thing. The other thing is there is a need for a broad memory-to-memory interface, ultra-low latency between processing and memory elements in a chiplet subsystem. And this one really needs as simple an interconnect as possible. We call our stuff internally basically just a bunch of buffers, because really that's what we're trying to achieve. So, but we think we've got a good answer to this problem. So here's what we're going to talk through. Some of these are one slide, some of them have a couple to it, but here we go. So here's what we want. Here's what we envision: a truly open ecosystem accessible to all players, from the garage startup to the larger companies. Basically, you put together a system on chip or a system in package, just like we used to do building printed circuit boards. Pull parts found from a catalog, integrate them in, lay it out, get it manufactured, and you come back and start verification. To do that, you need to have a source of chiplets available from multiple players, from chiplet OEMs, something that Crossfire wants to do, from IP providers who will eventually come to see, I believe, chiplets as another delivery mechanism for their intellectual property, and will productize it accordingly. And then we need interconnect densities that approach on-chip interconnect for this processor to memory interface. A lot of the larger pieces of IP, that interface isn't appropriate, and bunch of wires is a much better solution, or UCIe. But ideally, we get to the point, as a marketing guy, I think in terms of market segmentation, and there's a phrase, micro segmentation, where you're able to really hone in on focus on smaller and smaller markets. To do that, you need agility and velocity and the capability to tweak a design at a very low cost. Ideally, you get down to where you got a custom design for each customer if they need it. And that's where I think chiplets can get us. I won't spend too much time on this. We all know the answers here, but just to keep us on the same page and set a framework, we either do more, we do the same thing for less, we do both, and we enable quick tracking of the market. These are all the advantages that chiplets bring. Okay, so there are probably 3 different vertices you can think about when you talk about use cases. There is a functional use case. There is a horizontal use case, which is what I'm looking at here, which is what are the capabilities that you want to have for your product. And so I've come up with 4 different chiplet use cases that I'll talk through. The first is monolithic die disaggregation. The qualifier here being you're staying within the reticle. So what you're trying to do is to get better yield, or perhaps enable, excuse me, ability to change a small part of the die quickly if need be. And this is kind of what it looks like. And the little green box here is either interposer or substrate. That's important because eventually, frankly, we want to get rid of that. Technology optimization. This is where you are optimizing the semiconductor technology for the function that's in the chiplet. So this could be an A to D converter, maybe you use by CMOS, an SRAM block. Maybe you want to actually go to an SRAM type of technology with an interface on it instead of trying to use ASIC SRAMs for intensity. Or maybe you even do an embedded DRAM in this case. Deep submicron logic for processors, and so on and so forth. So I've tried to show this by color coding over here, where you've got different technologies represented by different colors that are then pulled together in an IP for a fictitious SoC that we're going to put together with chiplets. So beyond the reticle, in this case, what you're trying to do, and this is a touchy subject for some, it's also a complicated subject, and there are multiple approaches. A lot of people will use reticle stitching for this. That leaves you with a monolithic solution, but that's probably fine for a lot of people. I guess the biggest example of that is Cerebras. But fundamentally, you're trying to get beyond that 27 by 32 or something in that range reticle size. I'll leave that one as is and get over to the next set of use cases, which is, okay, we want to do domain-specific architectural type of designs. We want to focus in on a target vertical, a target use case, a target application, whatever the case may be. And so here what I've done is tweaked the design in the upper right, the technology optimization side. I've changed the 100 gigabit Ethernet interface into an OIF CEI interface, and changed the accelerator going into that supporting the custom instruction set architecture on the RISC 5 core, and swapped around the size of the on-chip memory and the L3 memory because the video transcoder down there at the bottom needs a different set of memory resources. That's what I mean about getting to domain specific or bespoke. You change around a few of the key chiplets, and then you're off to market. And then standards tracking. This is a huge problem for OEMs. A lot of times, a memory interface or a standard will change right in the middle of a product lifecycle, and all you really need to do is to support that memory interface. Right now, it's a respin of the entire device. So I think this is going to be one of the more popular things that chiplets get used for as we move along, moving from PCIe Gen 4, PCIe Gen 5, or CXL version 1 to 2 to 3, or whatever the case may be. So we've identified the problem. Let's talk a little bit about it. So as defined by the presenter, the interconnect pitch gap is the difference between the interconnect densities on an IC and the interconnect densities between ICs. And these have been lagging Moore's law by since the 90s, basically. I mean, it's always been a problem. I just picked some representative examples. Obviously, each technology, these numbers are different, but to kind of give you a ballpark area. So for TSMC N7, metal layers 0 through 4, you're looking at a 40 nanometer pitch. That's local interconnect, probably more relevant, and what I've highlighted is more of a regional or global interconnect, and that's 5 through 9 at 70 nanometers. And then in M10 for long runs, that's 124. There's also an M11 and 12 I didn't put here. It's basically for power strapping. It's 700 and some odd nanometers. And then let's look at the inter-die interconnect pitch. So starting off the far right, we've got AIB and EMIB, which is currently at 55, with roadmap going down to in the 40s and then the 20s. Info L is at 25 micron, and CoWoS HD is at an amazing 1.6 micron. I'm not sure how much of this is actually shipping, if any, but it's the best thing that I could find. So you look here and you see, okay, there's a 20 to 1 or more gap between high density interconnect on the die. Now, ideally, what you want to do when you're doing chiplets is to abut them up next to one another, interconnect at the same density. Obviously, that's impossible, but we think we can get it pretty close.
Sorry, one question, if you don't
Yes.
mind. If you go back to, this is the basically wire pitch or it's a bump pitch?
This is the bump pitch. So for Info L, I think the actual wire pitch is sub-micron. And AIB, that's a 2-micron trace in space is a typical implementations that we've seen. CoWoS HD, I'm not sure what that is, but this is the actual pitch, which is the spacing in between bumps or pads in an array.
Thank you. And
Okay.
also, can you share, if you know, or it's a public information, the number of layers, the maximum number of layers available for Info L and CoWoS HD?
I do not know that off the top of my head. That's a good question. Typically, what jumps into my mind is somewhere between 2 and 4. But
yeah, that's what I remember. I think Info was 3 with the promise that they're gonna get to 4, but I wanted to see if there is any new update on that.
Mm-hmm. Yeah, not that I'm aware of, and in particular, the research I did on CoWoS was fairly brief. I was more interested in the pitch, but the number of layers is obviously relevant, along with the trace in space. I remember the CoWoS trace in space being pretty dense, but a lot of that is deceptive because vias matter, and if you every time you put down a via, you're blocking routing tracks, and the vias are typically significantly larger than your trace and space pitch.
Thanks. Thank you.
Yeah. More questions? I mean, feel free to interrupt me at any time. I'm kind of going through this a little quicker than I thought I would. So, all right. So let's talk about registration error. So what is it? And I will comment that this is a one-dimensional picture. Trying to do this in 2 dimensions was not something that really played too well on PowerPoint, but I think we can envision our IP is 2-dimensional. We have a roadmap to 3D, and almost everything you see out in the wilds is going to be 2D as well. This is just to try and introduce the concept. Most of us will already have it, but I find that it's very useful just to go through that. So ideally, you can abut 2 chiplets together and just place them perfectly, and then get the interconnectivity down to very, very low. Maybe not quite making on chip, but close to it. But here's the rub. Once, and I don't know if it's going to let me play this. This sometimes happens. Some of these sharing programs don't let you do builds. And I think this is going to be the case. So what I want to do is, here's what happens. As you move this over here and this over here, this is kind of the worst case registration error. If you have this, start shorting out traces and pads, right? It's very much a no-go. This is the real world. So what do you do with this? Well, you have to increase your pad size until you've accommodated the worst case X and Y on the registration error. And then when you're doing arrays, you also have to deal with this in 2 dimensions. So that means you need multiple levels of interconnect or some approach. But your maximum pad size is mostly determined by the registration error. Secondary effect is the width of this trace. So that's registration error. Now, we call it registration error adaptation, registration error correction, whatever you want to call it. So this is our IO. And
wait, could you go back for a second? What is the actual definition of registration error?
Registration error is the uncertainty in the target placement of a die when you're building an array of chiplets versus the actual
Oh, I see. Okay.
positioning, right? So like we use a Shibura to place our larger die, and it'll do anywhere from and you know, and they give you a 3 sigma number, right? But you're looking at something around 5 to 7 micron accuracy, plus and minus X and Y. And there's also a theta component to that too, which a lot of people don't talk about, but is really could be throw a wrench in the works as far as where you want it to go versus where it actually goes. If you're talking about pads, or I mean bumps instead of pads, it's the same effect, only you have now pads that are landing, or bumps that are landing on the wrong pads where you're being mated together. So sorry, I should have made that clearer.
So you have 2 things. One is this idea of the density, the bump density gap, and the second is registration error. Those are your 2 things that you're trying to address.
Yeah, well, and they're very tightly correlated, because most of the issues with creating interconnect densities that are close to on chip are related to registration error, and then the others are related to how you process the connectivity. So what we do in our process, we use back end of line semiconductor equipment. So we're able to get down to trace and space densities. We can go down as far as the lithography goes, right? So if we use current lithography that's being used to manufacture deep submicron chips, we can get connectivity when combined with the IO that is going to match or come close to what's available on chip. But it takes both. It takes the lithography, it takes an ability to reconstruct a wafer that is planar, that is processable by the steppers and all the handling equipment, and it takes a way to unravel the effects of the registration error. So there's some more builds here. We call this a system of aggregated chiplets. And fundamentally, if I had my builds working, what I could show you was how you would build this SoC from these chiplets. All right. Now this has several advantages, obviously. You can mix and match these chiplets. This is a die shot of a graphics chip, as I recall. Very typical type of a implementation that you would see. So what I did was I defined a quad or a triplet here as these chiplets, and then you just build this up, and then this white area represents the interconnect between the chiplets, and it's a combination of our lithographic techniques and the Crossfire I/O. So the technology is patented between the assembly and the I/O itself, but we think we can get down, 50 to 100x denser than current solutions. It's really a matter of lithography. We can get down to almost where the lithography is printing the traces and the pads at. This enables higher power, a lower power, higher performance, and I'm going to throw a number out there power-wise that that my CTO believes. Well, we think we can get down to sub 50 femtofarad per joule or per bit. I mean, 50, not 50 femtofarads, 50 femtojoules per bit, transferring data die to die using our technology. That means that we have control over everything. We have control over the design. We have control over the I/O buffers, everything. But we've done a lot of work looking at this, doing some modeling, and we think it's there. It's all physics, right? The smaller your pads, the smaller the capacitance that you have, and the lower drive you need from your buffers. It just all plays out nicely.
Would you be able to say what kind of packaging you are like using your technology with? Like, it looks like it's once you get to these very fine lines, and you've mentioned things like CoWoS and so on. Is this for like a silicon interposer type assembly?
Well, you can use. I mean, it's a very good question. So I'll show some examples a little later on of some of the things that we've done. But fundamentally, the answer is yes. We can apply RDL on top of the interconnect and bump it, and you can use it on an interposer. You can assemble it onto a substrate, depending upon the complexity of the device, how many signals in and out of the actual package part that you need. Ideally, what we're trying to do is to allow our customers to create something that you basically bring in power, you bring in some of the larger buses, 100 gigabit Ethernet, that kind of thing, and everything else is handled internally to the device. Now, there are obviously issues with that. There's a ton of power issues you got to worry about. It's one of the biggest challenges that we found that we faced. And then power in is power out, so you got to get the heat out. Copper helps with all of that, and we have some new materials that we're looking at that will help with that. Power quality is important. So it's all a system level design problem, right? So what we're trying to define here within Crossfire and build is a kind of a demonstration vehicle for our technology. The idea is to use as many existing die or chiplets as possible and put them together in something useful. Initially, all of the I/O will have to be in what I'm calling a bridgelet. But what we have the capability of doing is adding RDL onto a device with larger interconnect, and then putting a bump pattern down that we can then interconnect with our bridgelet, just to demonstrate that things work, and to ideally in the long term, you would have I/Os on either side integrated into the chiplets, and you wouldn't need the bridgelets. And then these are just some of the things that we think would be an interesting addition. I don't think we're going to hit all of them, but right now I'm most focused on the FPGA chiplet. We're calling this the application programmable array instead of a field programmable array, because the idea is it's part of a chiplet that's application specific. Typically going to work with a processor either as an instruction set coprocessor, as a preprocessor to resources already on another SoC. But the possibilities are really really endless.
Wait, so are these your chiplets or third-party chiplets?
But right now, this is a concept.
Okay.
I am finding out what is and isn't available in the market at the moment. So in particular, looking at the FPGA space, where a big advantage here is block RAM. One of the hardest things to get right in an FPGA when you're specifying it is how much block RAM do you need, because it's very application dependent. So we think we can, in our application programmable array, enable a customer to go through and tune their design and figure out just how much memory that they need, and then build something that, pulling from a chiplet RAM catalog, can get very close to their requirements. So it's optimized. In some cases, right, it may not be worth that, but in other, everything's gonna count, and we want to be able to support it. The RISC-V processor, there are several examples out there, so we would probably want to use one of those.
Why do you show UCIe or BO as separate chiplets rather than as part of the chiplets? Or is this that, what's the thinking there? That
the thinking there is that something like a gigabit Ethernet interface or a PCIe would bolt onto this via a UCIe and bunch of wire interface.
I see.
Because that goes back to the technology future-proofing concept.
And one last, what is the sort of map from this to what Intel's EMIB is? Then they sort of show similar pictures. So in terms of,
it's a very similar concept. TSMC also has something they call a local interconnect bridge, I think it is. The difference is that the I/O density on this would blow either one of those solutions away.
got it.
And the power consumption once you have the Crossfire I/O design on the die integrated into it, instead of the phase one is just demonstration vehicle. To get to phase two, something useful, we would need to be doing some designs where we integrated that in.
Sorry, can you comment how many of lines you are getting per millimeter?
We feel like this is a great question for CTO, and I apologize, I'm not better prepared for it, but we feel like we can easily on a beachfront get 10,000 per millimeter.
And over one layer or multiple layers?
Well, that would be a 2D. So we'd have to look at the specific interface and configuration, but it would be with at least a couple of layers.
Thank you.
Hmm? So the Crossfire I/O, the Banyan I/O, as I like to call it, as is typical on test chips, you try out various parts of the technology, and that's what we've done. We've got a couple of sub-functions that we've seen silicon in, and we're doing a concept demonstration under development now that ties the rest of it together. The bridgelet's in definition. We're targeting a MPW run in November. The FPGA chiplet, where we're currently defining this, I'm talking to a couple of vendors, trying to see what works, what doesn't work. The RISC-V chiplet, we fully expect to find one out there in the wild. I mean, RISC-V is so popular. We even created on a contract an ASIC version of the SWR VL2 core, which, if there's something already out there, we don't want to spend resources developing it, but There's also been some thought about maybe we include it in the APA. There's some pluses and minuses on that. Where we're at as far as manufacturing, we're able to deliver prototype quantities of aggregated chiplets. We manufacture those in 2 locations, one in Fargo, North Dakota, at a NDSU facility. That's DARPA, for whatever reason, poured a bunch of money in up there, and there's actually some very nice capabilities up there that we're using. And then we also use other for hire. We're totally fabless quantities. We don't want to be a manufacturer in the long run. We're doing the development ourselves because we need that control. But essentially, we're not in the manufacturing business. We're in the chiplet business and the IP business. So we're currently talking to people. Anybody knows anybody that might be interested? We'd love to talk to them. So that's.
Hey John, what is the substrate? I mean, everything's very basic that you've disclosed, but
Yes.
something has to tie all this together, right? So there's a wafer of some type. It needs to be processed with the bridging information, right? And then all these other chips go on top of that. How do they connect to that wafer?
Right.
So how is this different from, a silicon interposer, for example, right? Because that's exactly what this. I mean, that's basically what this is, right? This is so.
Well.
And how is it low cost, or is
sure,
or is this not meant to be low cost? This is meant just to be for very high performance kind of applications. So I'm just trying to understand that.
Yes. So you're a great straight man. I have a couple of pictures I'll show here in just a second. So first of all, and this is hard to understand at first, is there is no substrate. The die are embedded. If you want to think of a substrate, the die are embedded in a substrate. But realistically, that's not even quite accurate. Let me show you. Okay, so this is the die and aggregate chiplet. I can't tell you how we do it, but I can show you the end example. So hopefully you guys can see my cursor. So what we're looking at here is this is actually a power supply module proof of concept that we did. So this doesn't have to be big digital. This can be mixed signal, can be analog, whatever. So in this case, there is one silicon die. There's a space that we left in the footprint for another die for a feature enhancement. And then this is fundamentally an AC to DC power converter. So there's almost 40 passive components, 17 die. And what we do is we use a pick and place machine to build a reconstituted wafer. And we place the die, and then we fill in the gaps with some of our proprietary materials that we use. And when we're done, this is its own subassembly. So there is no substrate under it. It's planar on one side. It's as planar as a silicon wafer. If you take it and slide it across the window, it goes like a hockey puck, or across the table, I mean. So that's why I say there really is no substrate. Now you can mount this onto a substrate if you want to.
Yeah. Okay, got it.
Right.
Very clever.
But it's one thing about our CTO is he's a very, very clever guy. And then we just metalize it, right? We go through, this particular one had 4 layers of metal. I think we did 3 front side and one back side to do some RDL. And I'm pretty sure we're showing the front side or top side connectivity here. And then just to give you an idea about the size of this particular item. We like small because it's good for yields. This is a semiconductor process, so you're looking at, in volumes, the economies of that scale semiconductor processing. So in a 12-inch process, putting down 4 layers of metal, vias, this is going to be pretty economical. This is a system and package device that we did. We also have a thin film interposer that we developed that's in our technology portfolio. We're really not emphasizing it that much, but what we have found out we need to do is to mount it onto a substrate for power delivery purposes, because it's signals and traces and power traces have much different requirements there. But in this case, this was a FPGA with a DDR4 memory subsystem, and then some minimal amount of on-board power conditioning and a termination resistors on the interposer. And this is what we would call a die last, typically in the chip last in the industry. We mounted the FPGA. We processed the DDR die ourselves, so we have a technique where we take the DRAM die and then just do an RDL on them. I mean, it's you know, we did our own. We probably for various reasons, process development, maybe. But you know, that RDL is no big deal, right? I mean, people do that and have done it for a while. And then in this case, just to kind of show off, we put it in. This is a 625 ball footprint, 17 by 17, and a 0.65 millimeter pitch. It was actually a bear to kind of work with on the printed circuit board. What input we got back from the OEMs is that's too dang tight.
So I don't get how the placement error problem has been addressed.
Oh, this is not anything to do with the placement error problem.
Oh no, I mean the previous slide in number 16 or 15, wherever.
Yeah. In this case, you don't have to, like I said, this wasn't big digital. So when you're getting into where you're putting a lot of, so that's a good point, Bobby, and I should have made it. In this case, we're only using one of the two techniques. So here, what we're doing is we're just reconstructing a die out of aggregated chiplets or dilets. And I'll use dilet as a term, as an unpackaged die that's meant to be packaged to separate it from a chiplet. Just kind of has a different use case. So in this case, this is something that we can do right now and support whatever IO densities. Like, for example, we could do an AIB design doing something like this because it's such a tight pitch. And yeah, in this case, the first step was to get this part right. So we weren't doing the registration error correction on this because we're well within the ability of the density of the interconnect to not have to worry about the registration error.
But what was the proposal on how it gets fixed?
Oh, that's using the Crossfire IO on different die to accommodate for the registration error. That wasn't needed here. None of these die. These are mostly analog die.
Okay.
So that's why there's no registration error. This is a just showing the aggregation process, which is step one of the two-step process to get to where you're correcting the registration error. And so when I talk registration error, this die will be placed down with a registration error, but the traces connecting it to these devices and to these components are the pitch there accommodates the registration error. It's kind of like that example I showed where the pads are big enough that you don't have to worry about it. That's in some cases that's good enough. But for chiplets
So,
and for, go ahead.
I have a question. This sounds pretty similar in tendency towards fan-on packaging, and for example, from DECA, their adaptive patterning. Is that going in the same direction?
Not really. What DECA does is, and it's very creative, but they use for each individual chip and each individual wafer, they change the routing based on the placement of the parts after they've been put into their carrier array. And so you have to go through and calculate that for every, basically you're doing a new mask for every device on the wafer. And then they use some e-beam type of lithography techniques to actually make those connections. Now that has some limitations as far as how much area you can correct, because you start having angles that if you're trying to correct too much, the traces will start overlapping one another. So I think right now I mean, someone may have a better number than I do, but I think in production, they're at around 10 to 20 micron. And they're probably 20 micron pitch, 10 micron traces, something like that. I mean, I don't take those as hard, but that's sort of the ballpark about where they're at.
Yeah, okay. I think even with the public numbers that they have there, they're more towards like 2 microns and below. But the
Okay.
idea is certainly correct. So then I guess contrasting that to what you do, it sounds like you're basically compensating for misalignment in another way, possibly in like within the silicon, to make sure that in the end the connections go from the right point to like right A to B in the designated chiplets.
That is true, yes. And it's really applicable to the processor, the memory interface, as much as anything, right? Because there you want very broad, I mean, ideally thousands, tens of thousands of connections.
So John, just for so if I'm comparing this to, let's say, a standard organic substrate, which is well-known technology and everybody's using 130 micron pads,
right?
Where the registration error effect is minimal, then this is clearly not really a replacement, right? This would be a replacement for people who are really trying to push the technology. And to your point, if everybody was at 5 micron pitch, I'm just using an example, right?
Sure.
When we're a long way from that, then the registration error of connecting all these chiplets is a huge deal. And you have a way of addressing that. I'm just trying to put it in so this would be a sort of very applicable to the more advanced packaging issues, right? As opposed to
absolutely,
right.
Yes.
And then finally, is this also applicable potentially to 3D, or is this more just for 2D?
It's very applicable to 3D. Yeah, okay. We haven't implemented the 3D version yet, but it's on our roadmap, and we know how we're going to do it. And that's where it gets interesting in things like die bonding, right? Because even the pitches there at die bonding are limited to in the micron range right now. But we feel like we can going 3D and mounting a die like that we can get down sub-micron pretty easily. It's going to take the I/O on both die to make that happen. But it's very, very feasible.
Okay, got it. Thank you.
And very good summary, by the way, Kash. That's you nailed it. Speaking of the current interposers, 130 micron pitch. Yeah, that's exactly what this technology was designed to implement. We've figured out a way now to kind of handle those types of pitches, which are larger, believe it or not, than what we typically want to do on the die aggregating process. But this interposer had some really, really good electrical capabilities. I did all the signal integrity simulations and hyperlinks on it, and it is amazing. It is amazing. This
Wait,
basically.
But pardon me for missing the obvious, but why do you need an interposer if you have your bridges? It doesn't matter what's underneath there, right?
Yeah, and I'm mixing metaphors here a little bit. This is more of a system and package concept, which we're taking the learnings from that and putting it into the new focus for the company.
I see. Okay.
Yeah, and sorry I wasn't clearer about that, Bobby. That's a good point, a good question. Yeah, this started out. We were trying to build a drop-in replacement for a Xilinx FPGA, only it had the memory system on it, because talking to their customers, getting the memory system working is a bit of a chore. It's typically a 12 to 18 month effort to do that. This is just another look at interposer on board. And again, just to look back, this is not our current focus. This is just some of the things that we did in the path moving forward to where we're at now. I mean, that said, if someone had an interest in working with us on this thin film organic interposer, we would we put a lot of time and money into it. We wouldn't be, we'd be willing to talk. All right, so I'm going to pause for questions, and then I want to kind of move away from Crossfire and onto what we learned and what we can share about what we learned and the things that we've done the last few years.
We're down to 7 minutes, so maybe it's worth zipping to those right away.
Okay. All right. So when you're working with chiplets, you're working in two worlds: the chip design world and the board design world. And these are different people that think differently, and it's bad sometimes. Two experiences that we had to do simulations, we needed IBIS models. So our FPGA vendor generated IBIS models for a particular design because the IOs are programmable. So there was a generic model that then you went through the tool suite and they would kick out an IBIS model. So we were doing two things. We were working with the die, and second, we needed to be able to deal with all of those components. So we wound up having to take the raw data and build an IBIS model for each one of the die, because that was our unit. We weren't dealing with just 784 pins package, for example. We had several thousand pins in the die to deal with. Same thing for the BSDL or BDSL. Maybe I made a typo. Boundary scan definition logic. Yeah. We found a nice tool that would let us do connectivity testing between our processor and our DRAM. But there were no models available for a die. So we had to go in and write our package models, the BSDL models, and modify them to their tool, which was a royal pain, because they were used to working with packaged DRAMs, packaged die, not DRAM die and FPGA die. So another thing was that we didn't think enough about how we were going to observe the signals in this interface. We thought just having test points with all the termination resistors on the DDR channels and would be enough. Well, it wasn't. So adding the BSDL types of continuity testing was helpful. The trick to doing that was there's a test enable pin on the DDR4 that you need to be able to make it configurable, and how to work that out in the system, get it into test mode and test out of test mode. It's one of the things that sounds simple, but you got to think through carefully while you're booting up the device. More so production test. When someone buys something made out of chiplets, they don't want to call up Xilinx, they don't want to call up Intel, or they don't want to call up Analog Devices or NXP. They want to call it, they want one throat to choke, and then those people deal with the vendors. So that means you got to have ability to onboard self-diagnostics. We're still away from getting to there. Another one that we ran into was the IO standards, and I'm going to pick on DDR4 here, for example. This standard is meant to drive server processors out of package across a large server motherboard into DDR packages, DIMMs. Way more complex. Our traces were shorter than most of the traces on the DIMMs that's at the end of this chain. So there's a lot of over engineering as far as drive strength, as far as termination strategies that you just don't need in a chiplet. So the EDA guys are working hard, but you know, we still got a lot of territory to cover here. And this is kind of how I like to close out the presentation. And for whatever time we have left for discussion or feedback, I'm either here now, or you guys are welcome to reach out to me separately. And by the way, thank you for your attendance and all the great questions. It's much appreciated.
Any questions? Thanks, John.
Poppy, back to you.
Thank you. Any questions for John? Actually, the slide 20 was really nice. Maybe, would you mind showing 21 again for a minute?
No, not a bit.
Got it. Thanks.
Yeah. Now, I guess if there's one thing I get up on the soapbox on, is this whole democratization concept. You know, Apple was started in a garage. It's impossible to do that unless you're trying to write some app of some kind in hardware. I mean, except in software, right? In hardware, it's very, very difficult because the barriers to entry are high. The economic barriers, the accessibility of the technology that is in there, even if you do have the money in the bank, still getting people to talk to you. They're evaluating you against their big customers, Google, Amazon, Meta, Cisco, right? And it's like, who are you? Go talk to a distribution. Well, you don't have distributors. Oh yeah, you figured that out, right? In other words, you know, go away. I mean, it's a challenge, and that's something that's why I've spent time with this group, because I think that we're enabling a new round of innovation in the hardware side with chiplets, and to me, that's exciting.
Agree 100%. That's a nice, bright way to end the call, since we're on at 9 a.m. on the dot. Thank you.
All right. Thank you for the opportunity, Bapi.